Have you ever wondered why engineers would deliberately design something inside your household appliances to break? If you open up a standard electrical plug, you'll find a delicate little component engineered specifically to fail. It seems entirely backwards to build a point of failure into a machine, but this weak point is there on purpose. It acts as a strict limit for electricity, making sure that dangerously high flows can't reach your appliances and cause a fire. We typically manage this electrical safety limit using one of two common devices: a traditional fuse, like the one found inside a plug, or a modern circuit breaker, usually found inside a home's main electrical panel. To understand how we keep electricity flowing safely, we're first going to look closely at how a tiny fuse physically breaks a circuit. Then we'll step inside a circuit breaker to see the clever mechanics that make it a modern alternative to the traditional fuse. By the end, you'll see how introducing a carefully controlled failure is actually the secret to keeping an entire electrical system completely safe. This diagram shows a standard electrical circuit with a fuse built straight into it. Inside that fuse is a very thin, carefully measured piece of wire. When too much electricity forces its way through a small space, it generates friction and heat. If the flow spikes to a dangerous level, this specific wire gets so hot that it actually melts entirely. When that wire melts, the physical bridge connecting the electrical path is gone. Without a complete loop, the electricity instantly cuts off, stopping the hazard in its tracks. But for this to work correctly, a fuse has to be installed in a very specific place. It is always attached to the live wire coming from the power source, and never the neutral return wire. The live wire is the one actively carrying the incoming electricity into the device. By putting the fuse there, melting it guarantees that the incoming power is severed before it can ever reach your appliance. Fuses are labeled with a limit measured in units called amps. You can think of an amp as the volume of electricity pouring through the wire, kind of like the amount of water moving through a pipe. A fuse labeled 13 amps is designed to melt if the volume of electricity exceeds that specific amount. Because the fuse works by physically destroying itself to save your appliance, it's a one-time use device. Once it does its job, that little glass tube is permanently broken and requires a physical replacement to get your power back. While a melting wire is incredibly reliable, replacing fuses constantly can be inconvenient. That's where circuit breakers come in. They provide the exact same safety net, but without the need for replacement parts after every power surge. This diagram outlines the inside of a circuit breaker. Instead of a sacrificial melting wire, a breaker uses an internal electromagnetic coil placed right next to a physical switch. Electricity flowing through a coil naturally creates a magnetic field. When a massive, unsafe surge of power hits, that magnetic field spikes instantly. This creates a powerful magnetic shove that physically hits the switch and knocks it out of its connected position. The sheer force of that sudden magnetic field physically forces the switch open. The electrical path is broken and the electricity stops flowing immediately. The major practical benefit here is reusability. Because nothing actually melted or broke inside the device, once you figure out what caused the power surge, you can simply push the switch back into place to reset it and restore power. Circuit breakers can also be manufactured with extreme precision. Let's see what you remember. To properly isolate a device from incoming power, which specific wire does a fuse have to be connected to? It always goes on the live wire to guarantee you completely sever the connection from the main power source. And finally, if a power surge trips your system, why is a circuit breaker easier to deal with than a blown fuse? Because nothing was destroyed. You can just flip the switch back on, avoiding the need for replacement parts. By deliberately building a fragile link into our circuits, engineers created a brilliant failsafe. These intentional breaking points stand as silent guards, reliably cutting the power so that our modern homes stay completely safe.